Imagine a place where gravity is so powerful nothing can escape, not even light. What comes to mind? Yes, a black hole. But what exactly are black holes? Let's dive into the fascinating world of these cosmic phenomena. A black hole, in the simplest terms, is an area in space where gravity is so immense that nothing can escape its pull. It is like an invisible cosmic vacuum cleaner, sucking in everything that ventures too close. But how do these fascinating and somewhat terrifying entities come to be? Black holes are born from the remnants of massive stars. When a star has burned out all its fuel, it collapses under its own gravity, resulting in a supernova, a stellar explosion that's so bright it can outshine an entire galaxy. However, not all supernovas result in black holes. Only the ones that were once supermassive stars end up as black holes. Now you may be wondering, why does nothing escape a black hole? This brings us to a fundamental concept in physics called escape velocity. Escape velocity is the speed that an object needs to reach to overcome the gravitational pull of a larger body like a planet or a star. On Earth, for instance, a rocket needs to travel at a speed of roughly 11 kilometers per second to break free of our planet's gravitational pull. But when it comes to black holes, the escape velocity exceeds the speed of light, the fastest speed known to us. And since nothing can travel faster than light, nothing can escape a black hole once it crosses the event horizon, or the point of no return. So, in essence, a black hole is a region in space where the gravity is so strong that nothing, not even light, can escape. These cosmic phenomena are a testament to the immense forces at work in our universe, a reminder of the endless mysteries that space holds for us to unravel. Now that we have a basic understanding of what a black hole is, let's delve a bit deeper into its structure. A black hole, in essence, consists of three main parts: the event horizon, the singularity, and the accretion disk. Let's start with the event horizon, a term that might sound like something straight out of a science fiction novel, but it's very real and possibly one of the most fascinating aspects of a black hole. The event horizon is essentially the boundary of the black hole, the point of no return. Once something crosses this threshold, it can never escape the black hole's gravitational pull. Not even light, the fastest thing in the universe, can outrun it. Now imagine if you were to keep going, passing through the event horizon into the black hole. What would you find? This brings us to the singularity. Quite simply, a singularity is a point in space where the gravitational field is so intense, its density becomes infinite. This is where all the matter that a black hole has swallowed up gets crushed into. It's like the ultimate cosmic recycling bin, where everything gets reduced to a single point of infinite density. But we're not done yet. Circling around the black hole, we have the accretion disk. This is a flat, rotating disk of matter that has been drawn in by the black hole's gravity, but hasn't quite fallen in yet. As this matter spirals in, it heats up and emits a vast amount of energy. This is often the only way we can detect black holes, as they themselves do not emit light or radiation. To sum up, a black hole is not just a simple hole in space. It's a cosmic beast, with a boundary that once crossed leaves no chance of return, a core that crushes matter into an infinitely dense point, and a swirling disk of doomed matter emitting a desperate cry before its ultimate demise. In the heart of a black hole, under the cloak of the event horizon, lies the enigmatic singularity, a point of infinite density that defies our current understanding of physics. Did you know that not all black holes are created equal? Yes, there are different types. Let's dive into the cosmic world of black holes and explore their fascinating variety. There are three main types of black holes: stellar, intermediate, and supermassive. Each one is unique, possessing its own set of characteristics and quirks, all based on their size and mass. First up, we have stellar black holes, the most common type. They're formed when a massive star collapses under its own gravitational force after running out of nuclear fuel. Stellar black holes have masses up to 20 times greater than that of our Sun, but they're typically about 10 miles in diameter. That's roughly the size of a large city. Yet they pack a punch with a gravity so strong nothing can escape, not even light itself. Next, we have intermediate black holes. They're the Goldilocks of black holes, not too big, not too small, but just right. They weigh in between 100 and 1,000 times the mass of the Sun and are thought to form when stars in a cluster collide in a chain reaction. Though they're elusive and not as well studied as their counterparts, They provide a crucial link in our understanding of black hole evolution. And finally, there's the supermassive black holes, the cosmic giants of the universe. These behemoths have masses millions or even billions times greater than our Sun and are found at the center of nearly every large galaxy, including our own Milky Way. Their origins are still a bit of a mystery, but some theories suggest they might have formed from the accumulation of many smaller black holes and massive stars, or from immense gas clouds at the dawn of the universe. From stellar to supermassive, each type of black hole presents its own intriguing set of properties and mysteries. As we continue to gaze into the cosmic abyss, who knows what other secrets these celestial phenomena are waiting to reveal? Ever wondered what happens to space and time near a black hole? Brace yourself for a mind-bending journey. In the vast expanse of the cosmos, black holes are unique. These fascinating objects do more than just sit idly in space. They actively interact with the fabric of the universe itself, space and time, distorting them in unimaginable ways. Imagine space-time as a trampoline. When you place a heavy object in the middle, it creates a dent. The heavier the object, the deeper the dent. Now, what if the object is so heavy that it creates a hole in the trampoline? That's what black holes do to space-time. This distortion of space-time around a black hole is so intense that it leads to some extraordinary phenomena. One of these is gravitational time dilation. According to Einstein's theory of relativity, the closer an object is to a massive body, the slower time runs for it. In the vicinity of a black hole, where gravity is immensely strong, time would slow down to an extent that is almost impossible to comprehend. If you were to watch a clock falling into a black hole, you'd see its hands slow down and eventually stop as it approaches the event horizon, the point of no return. But the influence of black holes extends beyond time. They also affect light. Black holes can act as a lens for the light from stars and galaxies behind them. This is due to a phenomenon known as gravitational lensing. When light passes near a black hole, the gravity of the black hole bends the path of the light. This can result in multiple distorted images of the same distant object, creating what are sometimes referred to as Einstein rings. These phenomena serve as a reminder of the strange and fascinating universe we live in, where the rules as we know them can be twisted and turned by the immense forces at play. Black holes, thus, are not just objects in space, but are active participants, distorting space and time around them. We've journeyed from the basics to some of the more complex aspects of black holes. Now, let's recap. Black holes, in the simplest terms, are regions of space-time exhibiting such strong gravitational effects that nothing, not even particles or electromagnetic radiation like light, can escape from inside it. They're like cosmic vacuum cleaners, sucking in everything that comes too close. But remember, they're not monsters lurking in the dark corners of the universe, waiting to gobble up unsuspecting planets and stars. They're just celestial objects following the laws of physics. Next, we delved into the structure of a black hole, which is as intriguing as its nature. Each black hole comprises three main parts: the outer and inner event horizons, and the singularity at the very center. The event horizon is the point of no return. Once you cross it, there's no coming back. And then there's the singularity, a point of infinite density where the known laws of physics cease to apply. Moving on, we explored the different types of black holes. Stellar black holes, the most common type, are formed when a massive star collapses under its own gravity. Supermassive black holes found at the center of most galaxies have masses millions or even billions of times that of our Sun. And then there are intermediate black holes, which are still a bit of a mystery. We then touched upon the intriguing relationship between black holes and space-time. Black holes distort space-time, causing it to curve, and this curvature is what we perceive as gravity. The stronger the gravity, the more space-time bends. Near a black hole, space-time is curved to the extreme, and time slows down significantly. From their formation to their impact on space-time, black holes continue to be one of the most fascinating and mysterious objects in our universe. As we continue to explore these enigmatic entities, who knows what new mysteries we'll uncover in the vast cosmos.